Hi, everybody. We're going to kind of pick up where we left off. So we're going to talk a little bit about, a little more about this idea that light has this quantized nature, where the energy that's transmitted by it can be delivered in these small packets. And what we want to do is we want to relate that energy to energy changes that occur inside the atom. So in the early 20th century, one of the things that scientists discovered was that if they looked at the light that was emitted by a single element, that they didn't see what they normally saw when they looked at the light that's emitted, like, say, by the sun. So you guys have all seen a rainbow before. So you know, like, if we take white light or sunlight and we pass it through a prism, that it'll separate out into all of the colors of the rainbow, and we see what we refer to as a continuous spectrum. All right. But if you look at light from a single element, so the two glass tubes that they're showing you here, one of them is hydrogen and the other one is neon. And what you notice right away is that when the gases are excited by applying an electrical current through them, that the hydrogen glows kind of pink and the neon glows kind of an orangey red. So furthermore, if I take that light and I pass it through a prism, I don't see the nice continuous spectrum that I saw for white light. So they're showing you a picture here of white light being passed through a prism, and we see this continuous rainbow. But if we take the light from a single element, instead of getting that continuous spectrum, we get what we refer to as a line spectra. So this is what line spectra look like. So back in the late 1800s, John Balmer looked at the spectra of different elements. In particular, he looked at hydrogen. So when you look up here, I'm going to try and grab the pen. So when you look up here at hydrogen, so let's just see if we can get that. All right, what we see is that there's only specific lines that are showing up. All right, this bottom scale that you see, these are wavelengths. So every time they looked at the light that was emitted by hydrogen, they saw a spectrum where each one of these lines showed up at a specific wavelength. And if I look at a different element, like the one underneath here, which is neon, I see a different number of lines that show up. So what scientists were able to discern was that those lines are essentially tied to an electron moving from one location in the atom to another. All right, so Balmer's studies were extended to include lines in the UV, the ultraviolet portion of the spectra, as well. And they were able to predict the frequency of each line by using the equation that you see that's written underneath here. So that 1 over lambda is equal to the Rydberg constant times 1 over Ni squared minus 1 over Nf squared. So I give you the value of the Rydberg constant there. The Ni and the Nf in this equation refer to the initial and the final energy levels of the electrons. So in other words, what this means is that as the electron moved from one position to another around the atom, they could calculate the wavelength, essentially, of the light that would be produced by plugging into this equation. So at this point, Niels Bohr made a proposal about the idea that the line spectra that they were seeing were being linked to the energy changes in the atoms, okay? And that energy changes of the electrons moving around the atoms could only occur in discrete packets at a given size. So he made two assumptions about the structure of the atom and where the electrons were, because it was the motion of the electrons that was causing this. So the first thing he said was that electrons moved around the atom in orbits that had fixed size and energy. So this is that planetary model of the atom that many of you have learned back in middle school and like that. So the idea that the electrons would orbit the nucleus of the atom much like the planets orbit the sun. And then the other thing he said was that if they changed location, so if they moved from one place to another, they had to absorb or release energy. So the Ni and the Nf that were in those equations that we just looked would refer to which orbit the atom was in. So the initial orbit it was in, the one maybe closest to the nucleus, and then the final orbit when it was further away. So this is a graph that's showing you these different positions. So over here on the right-hand side, there's a principal energy level. So these are the Nis and the Nfs. So down here at the bottom is the 1. All right, as you move up further, here's the 2. All right, and then so on and so forth. They go up from 3 up to infinity. So the idea is that as an electron moves from one of these positions to another, there's an energy change associated with it. And once I know that energy change, I can calculate the frequency of light using that equation E equals hf that we've used before. So what you can see is when an electron moves from a further location back down to the one closest to the nucleus, so if it goes from n equals 3 all the way down to n equals 1, all right, it would release a certain amount of energy. That's a lot of energy. And that energy actually falls in the infrared portion, or I'm sorry, in the ultraviolet portion of the spectrum. When the electrons move from, say, the third energy level to the second energy level, all right, this first green arrow here is showing me the amount of energy that would be produced, and these would show up as lines that I could see. So these would be the lines that I would be able to see on the line spectrum. So this is a very similar equation to the one that we looked at already. Instead of calculating the reciprocal of the wavelength, it calculates the change in energy. And then once you know the change in energy, you can calculate a frequency. But each one of these lines is associated with a specific motion of an electron from one of these orbits that Bohr described to another. So when I move further away from the nucleus, that would require energy. When the electrons fall back to where they started, that would emit energy. So at the same time that scientists were thinking about the idea that light had both a wave-like nature and a particle-like nature, they started wondering if they could apply this to basically everything. So the idea here is that if light can behave like both a wave and a particle, then maybe things that we've always thought of as behaving like particles could also behave like waves. So Louis de Broglie posited that light could have material properties, then matter should also have wave properties. And he demonstrated that relationship between mass and wavelength by using the equation that you see there on your on the slide. The problem is that most of the time the amount of the wavelength that we would see essentially would be so small that we wouldn't be able to detect it. And so even though we can predict these wavelengths for material objects, they're too small for us to detect. But when we start talking about an object like an electron, now we can come up with a wavelength that's associated with the motion of that electron. So this brings us to the Heisenberg uncertainty principle. And rather than explain the Heisenberg uncertainty principle to you, what I'm going to ask you to do is to go back into the course documents, and there's a short video that's posted there that talks about the relationship essentially between the momentum and the wavelength of an electron. So what Heisenberg did is he basically showed that the more precisely the momentum of a particle such as an electron is known, so momentum would be mass and velocity, then the less precisely I can know its positions. And so it was very difficult to actually determine exactly where an electron would be surrounding an atom. So what I want you to do is, first of all, I need to just stop and say this. You need to read this chapter. So there's a lot of information that it's difficult for me to kind of capsize for you. You need to go back and read it. You should definitely watch this video that talks about the relationship between momentum and wavelength for the motion of electrons. So we're left with a problem. So we feel pretty confident based on the Heisenberg uncertainty principle and de Broglie's ideas about the wavelengths associated with matter, that electrons as they move produce wavelengths. All right. The model that Bohr suggested didn't work well for atoms that had a lot of electrons in them. And according to the Heisenberg uncertainty principle, we can't really locate the electron exactly. And so what scientists did is they came up with a series of equations. In particular, there's a man named Erwin Schrödinger. And he basically came up with a series of complicated mathematical equations to determine the positions of the electrons surrounding an atom. So we're going to kind of talk about those. So the Schrödinger wave equations. Can't seem to move this. The Schrödinger wave equation. So Erwin Schrödinger developed a mathematical treatment into which he put both the wave and the particle nature of matter. And this is referred to as quantum mechanics. So the Schrödinger wave equations are used to essentially describe the location of electrons that are surrounding the atom. And we're going to talk about those wave equations, and we're going to talk about what they mean physically in the next video.